Have you ever scribbled a quick note, maybe a phone number, or a grocery list? And in that list, perhaps you wrote down the digit 7. It's instantly recognizable to you, isn't it? But what does it mean for a computer, a machine that only understands numbers, to recognize that same handwritten 7? How does it go from a messy collection of pixels to confidently saying, aha, that's a 7? This isn't just a parlor trick. It's the fundamental challenge behind everything from your phone unlocking with your face, to medical AI detecting anomalies in X-rays, to the study tools powered by AI that are revolutionizing how we learn. In this series, we're peeling back the layers of AI, not just to show you what it does, but to truly understand how it works. Today, we're starting at the very beginning, how a computer takes something visual, like our handwritten 7, and turns it into something it can process. For us, an image is a continuous flow of light and color. But a computer doesn't see that way. It needs to break down the image into discrete, measurable pieces. Think of it like a grid. Each square in this grid is what we call A and LT, span style equals color yellow, and GT, pixel and LT/span and GT. And for each pixel, the computer assigns a number representing its brightness. For a simple black and white image, a dark pixel might be a high number, say 1, and a white pixel a low number, like 0. So, our handwritten 7 isn't a 7 to the computer. It's a massive collection of numbers, a grid of ones and zeros, or perhaps values between 0 and 1 for shades of gray. This grid of numbers is the computer's and LT, span style equals color yellow, and GT, input and LT/span and GT. Now, how do we get from this grid of numbers to the confident declaration, that's a 7? We need a way to process these numbers, to find patterns within them. This is where the concept of A and LT, span style equals color yellow, and GT, neuron and LT/span and GT, comes in. Imagine our neuron as a tiny decision maker. It takes in all those numbers from our 7 image. But not all parts of the image are equally important for recognizing a 7. The horizontal bar at the top, for instance, is pretty crucial. To reflect this varying importance, our neuron assigns A and LT, span style equals color yellow, and GT, weight and LT/span and GT, to each incoming connection. A strong connection, like from a pixel on the top bar, gets a high weight. A weak connection, from a pixel in an empty area, gets a low weight. So, for each pixel value, the neuron multiplies it by its corresponding weight. This is like saying, how much does this specific pixel contribute to my overall decision, given its importance? The neuron then sums up all these weighted pixel values. It's collecting all the evidence, weighted by importance, from every single pixel in our 7 image. But there's one more piece. Sometimes, a neuron needs a baseline level of activation before it even considers making a decision. This is called the and LT, span style equals color yellow, and GT, bias and LT/span and GT. It's like a small, constant push or pull, independent of the input. So, the neuron takes the sum of all weighted inputs, and then adds this bias term. This combined value is the neuron's raw activation. But we don't want a raw number, we want a decision. Is it a 7 or not? For this, the neuron passes its raw activation through an and LT, span style equals color yellow, and GT, activation function and LT/span and GT. This function squashes the raw value into a more meaningful output, often between 0 and 1. For example, a common activation function is the and LT, span style equals color yellow, and GT, sigmoid function and LT/span and GT. It takes any number and squashes it into a value between 0 and 1. A very high input becomes close to 1, a very low input becomes close to 0. This final red number, the end LT, span style equals color yellow, and GT, output and LT/span and GT, of our neuron, is its confidence level. If it's close to 1, the neuron is saying, yes, I'm pretty sure this is what I'm looking for. If it's close to 0, it's saying, nope, not it. So, to recap our single neuron, it takes many inputs, multiplies them by learned weights, adds a bias, sums them up, and then squashes the result through an activation function to produce a single output. But one neuron isn't enough to recognize a complex digit like 7. A single neuron might be good at detecting one specific feature, like a horizontal line. But a 7 has multiple features, a top bar, a diagonal stroke, and specific angles. This is why we don't just have one neuron. We arrange them in and LT, span style equals color yellow, and GT, layers and LT/span and GT. The first layer of neurons might specialize in detecting very simple features, like edges or corners. Each neuron in this first hidden layer takes the entire image as input, but with its own unique set of weights and bias. One neuron might learn to detect the top horizontal bar of the 7. Another might learn to detect the diagonal stroke. The outputs of these first layer neurons then become the inputs for the next layer of neurons. This is where the magic happens. The network starts combining these simple features into more complex ones. A neuron in the second layer might take the output from the horizontal bar detector and the diagonal stroke detector and combine them to say, aha. If I see both a horizontal bar and a diagonal stroke in a specific arrangement, that's a strong indicator of a 7. This process continues through multiple layers, each layer building on the complexity of the previous one, until we reach the final and LT, span style equals color yellow, and GT, output layer and LT/span and GT. The output